All right, something happened with the video last time on chapter 6 and 7. Sorry I'm getting back to this really late. Hopefully you guys are able to watch this in time. But I'll just jump right back into chapter 6 and 7. Types of reaction. Identify the specific types of reaction: substitution, addition, and elimination. I don't think you're going to need to know details about addition and elimination for this specific chapter, but just be able to identify them. It's pretty simple to identify. So we'll say this becomes this. That is elimination. And addition will be the exact opposite. I don't know how to spell addition. That looks okay. All right. Kinetics and rate law. Understand the difference between a unimolecular and bimolecular process and whether a reaction is first order or second order. Understand what the rate constant means and how it tells you about the energy barrier for a reaction to occur. Cool. All right, so unimolecular, it usually involves like a single substrate molecule. For instance, with specifically substitution reactions, you could say this is like a unimolecular process because it only, like the first step, it only involves this molecule with the chlorine leaving. A bimolecular is like a one-step concerted mechanism, specifically in substitution. It's like a concerted mechanism where the nucleophile comes in and attacks the electrophile, and they collide simultaneously, and the resulting rate is dependent on both the concentration of this and this, so the electrophile and the nucleophile. So, as a general, the rate of an SM1 will be K, and then the molecule with the leaving group, so I'll label that A. So that will be the rate law for an SM1 reaction. For the SN2, it's always going to be dependent on both. We'll call that A again, we'll call that B. A and B, the electrophile and the nucleophile, because it's a concerted mechanism. It depends on that collision between those substrates. All right, understand what the rate constant means and how it tells you about the energy barrier for a reaction to occur. All right, the rate constant is K. And it's proportionality. It's like a proportionality constant in the rate law, and it relates to the reaction rate, like to the concentration. I don't know how to put that simply. Chem 106 or Chem 112 stuff where it's like the equilibrium constant. But what it tells you about the energy barrier. So a high K equals a low activation energy. Things that influence K, it's going to be temperature. A higher temperature equals a higher K. And catalyst. Presence of a catalyst can equal a higher K. And tying that all back to the activation energy or energy barrier, EA. Higher temperature is going to denote a lower activation energy. Presence of a catalyst will denote a lower activation energy. And to see that visually, oh, that was rough. We'll just say this is obsolete SN1 reaction, or SN2 reaction, sorry. From the bottom energy to the top energy, or wait, that's not right. That's the free energy. This gap right here is our activation energy. So a higher temperature, the line might look more like this. Catalyst, it doesn't always look smooth, but it's going to look lower. Cool. Be able to draw the mechanism for SN1, SN2. Include how the mechanism affects stereochemistry. So the basic is kind of like up here. I'll just do like a very generic SN1, SN2, and then I'm going to show you an example that might be difficult to say. If it's SN1, it's SN2. Ooh. So this is SN1 because the rate is dependent on the chlorine leaving this carbon group, this organic group, and it forms a carbocation intermediate that is always formed in an SN1. And then you're going to have the nucleophile come in at this step and attack the carbocation intermediate, and then that's going to form this. I like to draw like this. And then this isn't super stable because it's positively charged, or I suppose it isn't terribly unstable, but last step would be the nucleophile, or probably the solvent, which often is the same thing in an SN1 reaction, come in, take that, boom. So that's like the typical form for an SN1 reaction. I think these are like the typical 2 steps for an SN1 reaction, but it's always good to include everything, especially in the test. So that's the typical SN1. What does it say? Include how the mechanism affects stereochemistry. Oh yeah, because there's a carbocation intermediate. Because there's a carbocation intermediate, it destroys all stereochemistry. This nucleophile, if you think about this carbocation on like a planar, kind of looking like this, where, wait, no, that's not right. Where you can think of those dashes, or the wedges coming towards us, the dash going out. The carbocation, or the nucleophile, can come in and either attack the bottom or the top, which will produce a racemic mixture. So stereochemistry, racemic mixture. For this case, it doesn't matter because it's not even a stereocenter. SN2, I find it a little bit more simple. You're just going to have typically it's like a negatively charged small nucleophile, comes in, attacks the carbon, chlorine breaks off, concerted step. The rate law is dependent on the concentration of both of these. And there we go, yeah, that's right. I forgot to write the Cl minus over here, but Cl minus is always present. And that's the SN2 reaction. And how that's going to affect the stereochemistry, it's going to just reverse the stereochemistry. I'll try to think of a good example for that. Yeah, well, I suppose this would work. We'll do carbon-carbon. There's a Cl right here. And then so there's the stereocenter. If you count it out, it's first group, second group, third group. Right now it's R. This group will come in through backside attack. This will come off. What's the easiest way to do this? I think typically the easiest way to do it is if you have the one substituent on a dash, one substituent on a wedge, you can just put the nucleophile back where the leaving group was. So I'm just going to do that where this is OCH3. And then you can just switch this where it looks like that. And that's the hydrogen. Kind of just switch these two. That's the easiest way for me because like if I'm trying to do it conceptually and like flip everything so like the hydrogen is actually like on this side, I just get confused and end up doing the stereochemistry wrong. But you guys can figure out what the best way for you to do that is. So then this is going to be 1, 2, 3 hydrogens in the front. So you reverse it, it's an R, goes to an S. So stereochemistry is reversed. All right. I think I'm going to go to the fourth concept. Understand what conditions, base solvents, or alkyl halides are good for SN2 reactions. How do you make an SN2 reaction go faster? How do you selectively favor the SN2 reaction over SN1? Yeah, so this one is kind of tough. And instead of, just erase it. Instead of like going through like how to favor an SN2 reaction, I'm going to do more of a problem where I guess it could go by SN2 or SN1. So I actually sent you guys this neat little sheet where this kind of like shows you which conditions will favor an SN2 reactions, which will favor an SN1. And the sheet will be super useful for the next test as well with different types of reaction, like elimination reactions. But you don't need to worry about all the stuff I scribbled out red yet. So as you can see right here, a primary carbon will be, or alkyl halide will be favored, which is like this, over a secondary, which is like this, over a tertiary, which is like, oh, that's a secondary, that's primary, and then that's a tertiary. So this actually will never happen. SN2 will not happen if it's a tertiary carbocation, and SN1 will never happen if it's primary. So that kind of makes it simple, except for with secondary alkyl halides. And that's when you're going to have to use all these to determine if it's an SN1 or SN2 reaction. So I'm going to give an example right here. We're going to say this happens with, and so that methanol and your solvent is going to be H2O. So you could, because this is a secondary alkyl halide, you could go by SN2 or SN1. So because of that, you have to start off by looking at your nucleophile. If I go over to here, look at the reactivity of the nucleophile, a strong nucleophile favors reaction. So what makes a nucleophile strong? I also sent you an email with like a little sheet about that. Typically it's like a smaller negatively charged nucleophile is a strong nucleophile. So for instance, OH minus, pretty strong. OCH3 minus, pretty strong. What favors an SN1? It's not as affected by the strength of the nucleophile, but a weak nucleophile favors SN1 because it's not favoring SN2, if that makes sense. So a weak nucleophile will not be a charge, or it will be bigger. And yeah. So let's look at this. You can clearly see with those rules that this is a weak nucleophile, has no charge. So you could say it's probably going to go by SN1. But then you want to look at the solvent. We got H2O, which is a polar protic solvent. Go over here. Solvent. Aprotic solvents favor SN2 reaction if either of the reactants is charged. So this is not charged, but it's still not an aprotic solvent. So it's not going to favor an SN2. A polar protic favors an SM1 reactant if the reactant is not charged. So this is clearly going to favor SM1. That's where you can just go in here. You know it's going to favor SM1. And you already know the mechanism for that. You can draw it out. Where it forms this carbocation. That's a little janky. Comes in, attacks it, forms a racemic mixture. And then, lastly, often the solvent will come in here. Oh, that's wrong. Come in here and deprotonate that, leave it with the neutral charge. And then something like that. Cool. I think if you guys just look at this document, practice this, try out random practice problems, it'll start to make more sense if it doesn't already. Maybe one more thing. I'll draw a reaction coordinate diagram for that reaction, because SN1 is where it gets really tricky. So reaction coordinate diagram, I would not be surprised at all if this is on the test. It's always going to look like that. Progress of the reaction goes that way. Energy goes that way. So looking at this, to start off, the easiest thing to do is look at your final product, the stability of that, and the initial product. Now you know that the O, or carbon-oxygen bond, is going to be stronger than the chlorine-oxygen bond right here, which means that this is going to be lower in energy, more stable. So this is right here. Why is this so... There we go. That's too high. We'll say this is the initial product with the... something like that. Is that what it was? Yeah. And then this is more stable, so it's going to be lower. And then that's going to be the... And then you start off with the first step. This is going to be the highest energy step right here, because it's the rate determining step. Activation energy will be greatest with this step. So you can draw like line way up here and just go. Oh. Activation energy is right here. And this is going to be our transition state, where you kind of draw that bond partially breaking. And then you know that this is the carbocation. And then you go to the next step, where this comes in and attacks that. That's going to be significantly lower in energy, because this product is a lot more stable than this carbocation, even though it is positively charged. So you can draw a line probably down here. Something like that. It does have a positive charge, so it's still I don't know exactly where it would be in energy. It might actually be lower than this, but I don't think it needs to be that exact. And then you draw that right there. The activation energy is pretty small, and that's why it's not regarded in the rate, because once you get over this energy barrier, this one's negligible, and it just happens so fast that it's as if it doesn't have an effect on the overall rate of the reaction. And then transition state is where that is starting to form with the oxygen. And then this is that positively charged. And then, as you know, next step, solvent comes in, deprotonates that. Transition state. If that makes sense. I think you mark one thing that I forgot to do in this. I'm pretty sure you mark the transition states like this. Shouldn't there be 3? Oh, I didn't even box that one. So that is what the graph would look like. And then SN2 is more simple. It's just that one step, and the transition state will always be, I'll draw it for this one specifically, it's going to be, the transition state for that will be just chlorine is breaking at the same time of that OCH3 forming that bond. All right. Is there anything else I need to go over? What impact? Okay, the fifth concept is understand what impacts the rate of the NSM1 reaction. So the only thing that will impact the rate of an SM1 reaction is going to be something that impacts this activation energy, because that's the only thing that actually affects the rate of that reaction. Everything else is downhill, happens really fast. So anything that affects the energy of this transition state, which is the carbocation right there. Where is it? Right there.